Okay, so today I'm going to tell you guys about the Biot-Savart law. So a little bit of history. In 1819, Hans Oersted discovered that a compass needle is deflected by a current-carrying conductor. Biot and Savart, two people, conducted experiments on the force exerted by an electric current on a nearby magnet. And they arrived at the mathematical expression that gives the magnetic field at some point in space due to a current. Okay, so what is the Biot-Savart law? It essentially determines the magnitude and direction of magnetic field induced by a current-carrying conductor. And it's a generalization of Ampere's law, which relates magnetic field to an infinitely long, straight, current-carrying conductor. Cool. So, cool. I'll go through the derivation on the board later, but essentially the relationship is that the infinitesimal element of the magnetic field is equal to some constant times the cross product of, or the current times the cross product of the infinitesimal length of the conductor times the vector in the direction of the current over the radius from the length element towards the point of interest. Biot and Savart found that that constant was mu naught over 4 pi, mu naught being the permeability or permeability of free space. Cool. So we come up with this differential equation up here, which is dV equals mu naught I. I simplify the cross product here to dl sine theta over 4 pi r squared. Cool. And to the right-hand rule is extremely essential for using Biot-Savart law. Essentially, what you want to do is take your right hand, point your thumb in the direction of the current, and hold your hand like you're holding the wire, and then curl your fingers, and the way that your fingers curl is the direction the magnetic field flows. Cool. You can try it out for yourself. Good. Don't use your left hand. That doesn't work. Okay, cool. And, all right, so I'm going to run you through this simple problem on the board here. So, we want to find the magnetic field induced by this current-carrying infinite wire. Given that the current flowing through the wire is 4 amps, and the distance here between the wire and this point P of interest is 2 meters, we want to find the magnetic field at P. Okay, so we start with our differential equation that we found earlier. And what we want to do is integrate and pull out our constants. So our constants are I, mu naught, 4, and pi. And then our integral, so we're integrating from infinity up here down to negative infinity using our differential dl, which is the infinitesimal length of the wire, sine theta divided by r squared, which is this length here. So we can't really simplify, we can't solve this integral easily, so we need to use trig simplifications to plug in for something that we can solve. So we substitute r equals big R over sine theta. So we make r squared equals a big R squared over sine squared theta. And here we find that tan theta equals r over L. So we simplify and differentiate to get this. We plug both of those in here, and we still have our constants pulled out, and our new integral with our new differential is we're integrating with respect to theta from 0 to pi. And a bunch of stuff cancels, so the sine squares go away, one of the r's goes away, and we end up with our integral being the integral from 0 to pi of negative sine theta d theta, which goes to 2. So that 2 cancels this 4, you get b equals I mu naught over 2 pi r. So using that very simple equation, we plug in our current and our radius, and we get the magnetic field at P is mu naught over pi teslas, which is about 4 times 10 to the negative 7 teslas. Cool. I hope you learned a lot, and have a nice day.